What's up, Hadro, and welcome back to day 94 of me doing the NeetCode 150 challenge. So today we're doing our second NeetCode Medium 1D dynamic programming problem, and without further ado, let's get straight into it. Okay, today we get NeetCode Medium problem 213, House Robber 2, and it seems like we've solved this before. When did we solve this? June 20. Oh yeah. I remember before I started the daily NeetCode challenge, I solved every single one of the 1D DP problems and so on, because again, I love DP so much. But okay. Let's get straight into it. You are a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. All houses at this place are arranged in a circle. This means that the first house is the neighbor of the last one. Okay. Meanwhile, adjacent houses have a security system connected and will automatically contact the police if two adjacent houses were broken into on the same night. Given an integer array nums representing the amount of money of each house, return the maximum amount of money you can rob tonight without alerting the police. Okay. Okay, so it's basically the same problem as House Robber 1. It's just that you can't rob the first and last house at the same time, right? If anything, we could have like, you know, two DP functions. One which is like, you know, don't rob the first house. Another one which is like, don't rob the last house. Or if anything, we could like introduce more dimensions and so on, but like, you know, they're Boolean and so on, so it doesn't really affect much. I gotta think. Or can I add? Yeah. Yeah, if anything, I just have a Boolean, right? Like, if anything, I do def dp self, comma I, and I have robbed house 1. Right? And then here I'll just have as my base case, last house. No more homes left to rob. If I is greater or equal to, here we'll do self.nums. Nums self.memo is equal to this, and return self.dp from 0, comma, false. Right? Here we'll return max of self.dp is so case 1 rob yeah, here we'll just do self.dp of 0, comma, false. If I is greater or equal to length of self.nums, then we'll just do return 0. Case 1 is equal to rob house index I. 1 is equal to self.nums at index I plus self.dp at index I plus 2. Again, we must skip over the. By the way, House Robber 1, I did I went in more detail than usual to essentially explain my thought process and so on. So for the House Robber 1 stuff and so on, I'm just gonna kind of fly by it fast. Here we'll do robbed house 1 or I is equal to 0, right? So we'll take the current result of this, or if I is equal to 0, we're robbing house 1. Okay. Case 2, don't rob house at index I. Case 2 is equal to, we'll do 0 to indicate 0 profit, but plus self.dp, we can go from I plus 1, and we'll keep the same robbed house of 1, right? Can only do so if we're base case number 2, if we're at the last house and chose to rob the first house, we cannot rob this home. So if I is equal to length of self.nums minus 1 and robbed house 1, then we'll say return 0. We can't rob any houses, right? So this is just a little bit of annoying OV1 logic to essentially get around it. And by the way, in terms of the size of the subproblems and so on, well, I guess this is like, 2D DP, but like really, this is a Boolean, right? So there's at most two things that it can be, right? So in terms of the number of subproblems, it'll be n times 2 is equal to 2n, right? If anything, we can probably write the logic in here to essentially make it, 1D DP, which I think we will do. Actually, that doesn't really help. But yeah. Res is equal to max of case 1, comma case 2. Self.memo of I, comma rob house 1 is equal to. So now we have 2 dimensions. It's equal to res, return res. And then here we'll do if I, comma robbed house 1 in self.memo, return that, right? So there's something like this work. It does. Let's submit. And there we go. Bada bing, bada boom. 0ms beats 100%. Okay, so here I'm kind of cheating per se, in that I don't know if this counts as 1D DP, where it's like obviously I have 2 variables and so on, but just one has n things that it can be, so it's definitely like, one dimension, and the other one is just a Boolean, right, which has like true or false, which is like, how O of 2n is essentially O of n. That's kind of my mentality here. It's just a bit of annoying logic to get around. I wonder if there's a better way to do this, right? The point is that, like, I'm going to have the same DP. Like, the convenient part of doing DP this way is that I don't have to look back at homes, right? So it's like, at index I, I don't have to worry about whether I robbed a house at index I minus 1 or not. I can just keep advancing forward and make sure that I don't rob a house I plus 1 if I rob the house I, right? The only case of going backwards is from the last home, right? So from the last home, I need to remember whether or not I robbed the first home, right? Which, can't really think of a better way than just like, passing it through the DP function, right? It's just O of 1 extra work and so on. I'm adding an extra fake new dimension to essentially just make the problem work, but it's still the same time complexity of O of n, right? I wonder if this is allowed. Okay, I'll take a quick peek at NeetCode solution and see if he did it with just an index I. Let's just see that. So first of all, we'll mark this problem as solved. Let's take a quick peek to see if he did it that way, right? I just want to see the code. Df. Oh, he has a flag. And is the flag a Boolean? I don't know what's going on, but he does have a Boolean, it seems. I flag. Bottom up. Where's the bottom up DP? Something, something. Here it doesn't look like he has a flag or something. Okay, I'm not sure. Okay, it seems like in his 1D DP he has that kind of flag anyways and so on. Okay, so you know what? I don't even feel guilty and so on. So okay, NeetCode did the same thing and so on. Yeah, makes sense, right? In terms of time complexity, this does nothing, right? It's just the only reason why I'm like kind of is because like, this is 1D dynamic programming. So I'm like, oh, okay, was there a way to do this with just one DP variable? But it seems like his solution does the same thing I do anyway. So you know what? No guilt or shameful feelings here. So I'll just proceed. And so as always in our videos, I do a quick recap of how I was able to solve the problem. So for this one, it is literally house robber 1 from the last video. And I did a more detailed explanation than usual for that video in case you're curious and want to watch it. But essentially, otherwise, I did the exact same thing in that video, right? Self.nums is equal to num, self.memo is equal to empty hash map, and here I do self.dp of 0 with a false. So I'll explain what that false is, but otherwise, a lot of the problem is, right? Here's like my 2 variables. So if those 2 variables that I have with their exact values is assigned on my self.memo, I've computed the problem before, so return that result, right? Otherwise, at the very end, when I compute the result because I brute force through it, I will make sure that I cache that result before I return, right? Then it's like, okay, let's go through the base cases, right? So essentially, self.dp at index I will essentially be the maximal result from nums at index I onwards, right? So if I is greater or equal to the length of self.nums, how many homes do I have left to rob? Well, I have nums from index I onwards homes left to rob. if I is greater or equal to the length of self.nums, this will translate to just an empty array, right? So out of an empty array, how much profit can I take from robbing homes? Well, 0. There are no homes for me to rob, so it's just a default value of 0 in those cases because there's no homes left to rob, right? So that's my base case. Otherwise, it's like, okay, this is a special case. I'll ignore it for now, but essentially we'll say, okay, there's only 2 possible cases from an xi, right? I either rob the home or I don't rob the home. If I choose to rob the home, then I essentially get the profit for that home, so self.nums at index I. But now what I have to do is, okay, I have to go from house I plus 2, right? Because the house at index I plus 1 is directly adjacent to the house at index I, which I chose to rob. I cannot rob adjacent homes, so I must skip the home at index I plus 1. I must go on from index I plus 2 onwards, which is exactly what I do, right? Which maybe I don't even rob index I plus 2 and so on. Who knows, right? But the point is that I can start robbing from index I plus 2 if I so wanted to, right? This will just return me the maximum result from I plus 2 onwards, right? Now for this, it's essentially like, okay, I essentially have a Boolean value here that essentially tells me whether I robbed house 1 or not, right? At the beginning, I haven't robbed any houses, so I set this as false, right? But the only way that I can rob the first house is essentially if I choose to rob the house at index I and index I happens to be 0, right? So if index I is equal to 0, then it's like I make it a true, right? Otherwise, if it's not index I, then I'm just going to keep the current value for robbed house 1, right? Maybe I'm at index I is equal to 5, right? And it's like I chose to rob the house at index 1 beforehand. So it's just like, okay, I'll just keep this. Or if I is currently equal to 0, then it's like this is when I set it to rob. I did rob house at index 1, right? And then otherwise, I can choose not to rob the house at index I. If I choose not to rob the house at index I, then I get a profit of 0. I didn't rob any homes, but now I can start robbing homes from index I plus 1 onwards, right? In this case, we have that we don't change the value of robbed house 1, right? We are not robbing any homes, so we're not going to be possibly affecting the value of robbed house 1, so we keep it as whatever it is as was given to us, right? When we rob a home, it could be that the home we're robbing is the very first one, so that's why we add that little or extra check, right? Then at the end of the day, between these are the only 2 possible cases. Either I rob or not rob the house at index I and then recursively compute the best of the rest. And so I just take the maximum profit from those 2 cases, catch that result, and then just return that result, right? Sorry, I have a bit of the sniffles. Okay, and now in terms of the time complexity, it's going to be, okay, number of subproblems it will be n index I, 2 choices, house 1 bool, implies n times 2 subproblems, implies O of n subproblems. Time per subproblem of 1. Right? So here what I'm saying is like, okay, checking if something exists in a hash map is O of 1. This is obviously O of 1. This is obviously O of 1. Right? This is obviously O of 1. Recursive calls, like I said in my last video, we can think of them as O of 1 because we're going to multiply the number of subproblems by the time per subproblem. And so obviously it's like when we cache results and so on, we essentially unlock these guys for free, right? Because again, like I might solve the problem for I plus 2 onwards and this Boolean here, right? But whenever I compute it again, I will essentially be able to look up its value directly, right? So I'll only do the work once for every single subproblem that is possible in the worst case. So the time complexity is the running time per subproblem without accounting for the time it takes for a recursive subproblem times the number of subproblems, right? Time per subproblem times the number of subproblems is the overall complexity, but because we only do every subproblem at most once, otherwise we catch the result and look up every time we need to call it, we treat those as O of 1 when we do our analysis, right? So O of 1, we treat this as O of 1. Let's say again O of 1, O of 1, O of 1, O of 1. So we have an O of 1 running time complexity per subproblem, right? So overall time complexity O of n times O of 1 is equal, implies O of n, right? There we go. So that's essentially the point that I am trying to make, right? So that's why I do not feel guilty about adding an extra dimension here, which happens to be a Boolean, right? Because the point is like the number of subproblems that I'll have is for this index I will have, yeah, up to every single index instead of nums might be a subproblem. So I have n subproblems here, right? And now I'm going to multiply by the dimension of the number of subproblems here. But this is not another index or anything, right? This is just a Boolean, right? If I rub house 1, this will be true. If I didn't rub house 1, this will be false, right? But this is just a Boolean. It's either true or false. So in terms of the total number of subproblems, it'll be every single of the n index i's when this guy is false, and each of the single index i's when this guy is true. So there's n times 2 total subproblems, but n times 2 is just still O of n total subproblems. And then the type of subproblem, just like in house number 1, is O of 1. So my overall runtime complexity is still O of n. The reason I felt a little guilty about putting this is that technically I have 2 dimensions here instead of my DP algorithm, right? But this is kind of like, a fake dimension because it's just like, O of 1 total possibilities, right? Only 2 possibilities, it's Boolean, right? So that's kind of how it is. So essentially, this is the exact same problem as house robber 1. It's just that here I have an extra check where it's like, okay, I have this new dimension robbed house 1, right? Whether I robbed house number 1 or not. And then I check like, okay, if I is equal to the length of cell nums minus 1, this means I'm at the very last house, right? So if it's the case that I'm at the very last house and I robbed the very first house, then I say I cannot rob the last house, and since this is the last house, I will just return 0, right? So the point is that like now the first and last homes are adjacent to one another. So I remember that, and then I'm like, okay, if I did rob house 1 and I'm at the very last house, I cannot rob the last house, right? So I add that little extra if statement, so that way I can essentially keep the rest of the logic the same as house robber 1, and there we go. Bada bing, bada boom. And yeah, so hopefully that solution makes sense. And as always, let's make sure that we come in here and check the it seems like we've already checked the box. And so yeah, so again, like if that's a little bit confusing, I took the time to explain how I think about dynamic programming algorithms a little bit more in detail inside of house robber 1, which is the first LeetCode medium 1D dynamic programming problem that I do. And now for the rest of the 1D DP problems, I'm just going to go like, faster in terms of my style and so on. But I will be doing the very same exact ideas, right? Caching results, looking up the results if they're already cached. Otherwise, brute forcing through the problem. Usually there's only like 1 or 2 cases and so on. Or it might be O of n work, which we'll eventually get to. Like, for example, this is one problem that I know I have to do O of n work inside of the body and so on. So we'll get to see many more examples, but everything that is essentially important, I essentially covered inside of the house robber 1 video, right? This is exactly the same code. It's just that I add a little bit of extra conditions. Like here, it's like, okay, if I'm in the last house and I rob the first one, I cannot rob the last house. And so I keep track of like whether I rob the first house inside of every single DP call. So that way, when I get to the last house, I can use that information to dictate whether or not I can rob it, right? And so that's pretty much it. It's just one tiny little tweak to the code from house robber 1. And yeah, so hopefully that solution makes sense. And otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment. But otherwise, I'll catch you in the next one. So until then, ciao, my friend. Bye-bye.